In this video I'm going to show you how to discretize a continuous transfer function based on a sampling interval. Also how to check your partial fractions when you undertake the hand calculation. So here you can see on the left here, this is your continuous system where you've got g, the transfer function for the zero to hold, and also the transfer function for here g of s. So this is for your system. So this is the same example that we used in the previous video, whereby you undertook the hand calculations, and then you ended up after discretizing with this g of z here. This being your discrete transfer function. What I've then done is I've applied a unit step input, and here to this given system, both the systems, so I should say, and what I've got here is your continuous time output and also your discrete time output. And you can see, because we discretized the continuous transfer function with a sampling interval of 1 second, what the discrete transfer function effectively does is provide us information at every sample point or sample interval. So 1 second, 2 second, 3 second, and 4 second. So that would be effectively the information that would be provided to the control. So in terms of simulating that graph, getting that graph from MATLAB and discretizing your transfer function, what I'm going to do now is just open up the MATLAB windows. So here you can see, in terms of this MATLAB editor script, so just remember new script, and it'll open up this, and then this is where I've then populated the MATLAB script. And also make sure you're working in a kind of current folder or current directory of your choice. So clear CLC close all, we'll do the usual command, so it'll effectively close all graphs, clear the command window, and clear the workspace. So you can see there at the moment I've got a clear command window workspace, I've got no graphs open. So discretizing from continuous to discrete transfer function. So what here is g equals tf, so for transfer function, then in brackets, you can see here, and then in square brackets I've got 12 because that's the numerator value. If we look back, 12. The denominator value is 1, 5 and 6. So if we were to multiply this out, it would be s squared plus 5s plus 6. So the coefficients are 1, 5 and 6 for the second order. If it was, for example, a first order, and it had, maybe it was, I don't know, s plus 1, then you just have 1 and 1, or s plus 2, 1 and 2. What we're discretizing this with a sampling interval of 1 second. So what I've done here is I've defined the sampling interval t subscript s is equal to 1. And then gd, this is what I'm going to use my notation for discrete transfer function, is equal to c to d. So this is continuous to discrete, so that's effectively undertaking your discretization of the continuous transfer function, because in brackets you've got g, and then this comma, and then ts. So what this is going to do is undertake your discretization method using the zero to hold by default. MATLAB will use it by default, and it'll discretize this continuous transfer function with sampling interval using a zero to hold by default. So if I quickly run that, so if I go run section, there, you can see there is our discrete transfer function. What we can do is check the partial fractions. So in this case, b, which is the numerator, is 12. A is, in this case, you're probably thinking, oh, why is it not the same as that? Because what you've got to remember is, when we're checking the partial fractions, is when we're doing the hand calculations, you have that extra 1 over s. Okay, 1 over s multiplied by g of s. So in terms of the partial fractions, you've got an s that multiplies through by here. So all this is going to do is just increase the powers of what the coefficients correspond to here. So here this is s squared plus 5s plus 6. Here it's now going to become s cubed plus 5s squared plus 6s, and then it's just going to be a 0 here because there's no coefficient that it multiplies to. So just put a 0 there. And then in square brackets, p is equal to residue in curly brackets ba, which is b comma a, which is effectively defining the transfer function numerator and denominator. So if I run that, there you'll see it gives you your partial fraction coefficients, a, b and c. And then the final two steps. So what I'm going to do then here is apply a step input. Okay, I should say unit step input, because by default, whenever you put step like that, MATLAB automatically assumes that you mean a unit step input by default. So I'm going to apply a unit step input to g, so this continuous transfer function here, comma, and then I've put here in these, here I've just put a dash, so that's just going to give me a continuous signal, comma, GD, so I'm going to apply unit step input to my discrete transfer function, which is given by this, and then in here put 2 dashes to effectively, it'll give me a dashed line, so I can identify the difference between the continuous and the discrete transfer function. And then the graphical output values here. So these commands I'm not going to go through because you're going to be used to them. So effectively setting the size of the font size of the area, X, Y labels, legend. So determine the difference between continuous and discrete. The only one you probably haven't seen is title. So I'm effectively in the same way that I define X and Y labels, and I'm doing that for the title, and then grid on. So then let's just run the whole script now, and you'll see the graphical output that you saw on the. You now see the graphical output that you saw on the start of this video. Okay, just to remember, if you want to put it in your report, edit, copy figure, and it will get rid of the grey background. Edit, copy figure, and then when you go into your Word document, click on paste, and it will give you a figure that hasn't got the grey background. And so that's applying that. And just remember that it's the information at the sample points. That's the information you're effectively capturing with the discrete model. So what we have here now is 4 graphs with all that have been discretized with different sampling intervals. So if we're looking at the graphs here, we've got graph 1, 2, 3, 4, and remember those IDs. We've got sampling intervals for TS's, well, with ID of 1, we've got sampling of 2, ID 2, sample interval of 1, sample interval of 0.23 for ID of 3, and 0.01 for ID 4. So obviously, as you would expect, the faster you sample, the frequency that you sample, if you increase it, your model there is capturing more. It's capturing more of the information from the continuous model. So, for example, 2 seconds, it's not catching too much. 1 more, 0.25 seconds more, and 0.01. You can see that there's not actually that much difference between the continuous and the discrete model. So now what I'm going to do is I'm going to go back to MATLAB and show you how to plot these graphs. So this is the MATLAB script here, and you'll notice some similarities to the previous script. So obviously these 3 commands here are the same. Again, the continuous transfer function is the same one that we're using. What I've got here is 4 lines here that detail effectively continuous to discrete, so discretizing 4 different transfer functions. We're effectively developing 4 different transfer functions. So GD was the initial notation we used, and what I've done for 4 of them is just use 1, 2, 3, and 4 to differentiate the difference in them. C to D, so G, so every time we're using the same transfer function. However, what we are varying is the sample interval. So previously I defined this as TS, and then define TS above with a value. But as we're using 4 different values this time, I thought it's best just to directly input it in here. So 2, 1, 0.25, and 0.01. So what this will do, if I run that, you see then you get your 4 different discretized transfer functions, all with the different sample interval it tells you here, sample time it calls it. You can notice the values, the coefficients are all very different as well, and that's something we'll talk about in future weeks. So in terms of plotting these, so applying again a unit step input to these 4 graphs and comparing that to the continuous, that's what we're going to do. So let's first start off with figure, because we're telling it effectively we're going to plot a figure. And then what we're using in this command now is a subplot, and in brackets 2, 2, 1. And what this means, if you look at this, this is your first plot, this is your second, this is your third, and this is your fourth. So what it's doing is every time you can see that the first 2 numbers are consistent with all 4 of these. So that's effectively telling when you're telling MATLAB that it's a 2 by 2 graph. Hence you're going to plot 4 graphs. This third number here is the ID number that I spoke about previous. So when I said 1, 2, 3, and 4, that's you effectively telling it that you want here this graph to be plotted at the top left, top right, bottom left, and then bottom right. So that's telling it subplot, and then you're telling it you're doing a 2 by 2, and then where you want to locate that graph. This step is exactly the same, so I'm not going to go over it. You're effectively just applying a step input to the continuous transfer function, and then also your discretized transfer function. And this is the same for all 4, but obviously the ID for the discretized transfer function changes. Because what you're trying to do is plot all 4 of the discretized transfer functions on the 4 different graphs. And then again, X, Y labels are the same, legend, and the title. One difference though is you have to put this grid on and a hold. Oh, no, sorry, not grid on, hold on. This hold on effectively tells you're telling MATLAB, right, hold on, I'm going to plot another graph. Hold on, I'm going to plot another graph. Hold on, I'm going to plot another graph. So if we run this, you'll get the graph graphical output that you saw a couple of minutes ago. So just bear with it a few minutes. Here I've got the graph now. So again, here you can see exactly the same graph that you had before. Got the legend here, so continuous time, discrete time, and yeah, you can see it's exactly the same. So I hope this video has been useful, kind of just initially trying to get you into using MATLAB Simulink for discretizing a system. For when we just on the initial kind of MATLAB script we had where we could check the partial fractions, and I hope then it's been useful in terms of plotting graphs in terms of one output, and then plotting graphs whereby you have multiple outputs, in this case 2 by 2 on different graphs.